Okay, these one would consider then as radiators of some type. They are not radiators of the gravitational wave itself, but taken in conjunction, each as a pair, produce a gravitational wave here focused between the two. Now, that focus can change. It doesn't have to be right in the middle. For example, if these neutron stars were on an elliptical orbit, their focus would shift. It would not be midway between, as you know, it would shift around, and it would be closer to apofocus. And if indeed you got all the way down to a rectilinear ellipse, then the focus would be way back over by one of the neutrons, or the pair of neutron stars in orbit when they came very close together. So this can be varied. It can be changed back and forth. It also can be varied depending upon the direction of the force change that is exhibited at these points. In this particular drawing, the radiators, which could be a laser here and a laser here, going in opposite directions, or it could be a cluster or array of FRs pointed or operating in opposite directions, or some other type of mechanism. The point here is that this peanut-shaped radiation pattern can be shifted around from one place to the other, depending upon timing and direction of the forces that are here. That makes a very interesting concept, particularly if you have these far apart. Now, the other advantage of being far apart is the intensity of the gravitational wave goes as a square of the distance between the two radiators. And this, again, is a standard thing that one can find in various textbooks. So if you can put the radiators at a greater and greater distance, you have more and more power. One concept is to put one radiator on the moon and the other at the L3 vibration point on the opposite side. This gives an even larger distance between the radiators and even greater intensity for the gravitational waves. Okay, let me move on to the next one. Keeping in mind that you can change the location of the radiator, as shown here. Again, it's a peanut-shaped radiation. This means that you can move effectively the focus or the point of emanation of the gravitational waves around really at any particular location that you wish. Here, if you're, for example, interested in seeing something underneath a building, you would place your focus here and then a detector up here. If you're interested in surveying people maybe inside a building, you put the focus here and the observation point down here. Well, what do I mean by seeing? If there were some change in the gravitational wave based upon some intervening object or material, then indeed you can, quote, see something by various means, raster scans and all kinds of things. So the central issue here is, does intervening matter have any measurable or functional effect on the passing of the gravitational wave? Well, first of all, we recognize that the gravitational wave is extremely weak. That's very important. The second thing we recognize is it goes through all material things without change, at least without change in intensity. The scattering of a gravitational wave is very slight, at least in theory. There are a few things that change. We've just seen one that Wood discussed, and that is if a gravitational wave goes through a very peculiar piece of material, namely a superconductor, its refractive index changes, and changes dramatically, at least according to Lee and Thorne. So the index of refraction, or the velocity of the gravitational wave, can indeed change based upon that. But we really wouldn't be thinking, there might be some special circumstances where in a system that we wanted to detect there was a superconductor, but in general, probably not. Okay, so scattering isn't very big. The change in refractive index, while it could be large, but that's for very specialized material. That leaves us really with just a few things that might change, but paramount among those is a polarization. Now, if we go back to that picture I had before, and let me look, and this is where I'm going to call upon you to have a little imagination. Again, let's think of these as two neutron stars moving around on orbit. Now, just at this particular point, let's say they're right here, if you look in Landau and Lifshitz, when they examine this thing, that produces a figure 8 radiation pattern when they're just at this location. Landau and Lifshitz then moves them on that orbit, and the figure 8 then sweeps out this peanut-shaped figure of revolution, essentially the radiation pattern. Now notice, as it sweeps out the figure 8, once it gets halfway around the orbit, it's already swept out the radiation pattern. And then it continues around and sweeps it out again. This is one way of explaining why the frequency of the gravitational wave is twice the frequency of the orbiting objects. So as this particular radiation pattern is swept out, there is a change in its intensity in each direction. And again, giving rise to a peanut-shaped intensity pattern. But more important and more specific here, there's a polarization change. If you think of the classical idea of this neutron star creating low frequency, a long wave gravitational wave is produced, if it's rotating on a circular orbit, the amplitude is going to be the same all the time. You're not going to have any change in amplitude of the gravitational wave. What then do you see? What you see is the change in polarization as the objects orbit. And that's why if you look in the classical pictures that you get on the internet and so forth, you see a picture of a circle, and then you see how it's bumped like this and bumped like that as a gravitational wave passes something like the Laser Interferometric Gravitational Observatory LIGO. You don't see a change in intensity. What you see is a change in polarization. So the polarization shifts. The intensity stays the same. And sometimes you'll see pictures of sort of a spiral out there as a gravitational wave moves out, and you try and detect it with LIGO, Virgo, LISA, all the rest. Well, why is that important here? The thing that's important here is that polarization is in a plane perpendicular to this orbit plane that includes this line of centers. So if this line of centers is very well defined, the polarization is very well defined. And in the generators, in the gravitational wave generators, those positions are fixed, and fixed very precisely. So if the positions are fixed very precisely, the plane of the polarization is fixed very precisely and has a constant value, at least constant over the emission time of the high-frequency gravitational wave. If you go through all the calculations, you'll see that for this particular case, where I've shown geosynchronous orbits, and assuming that you have a good orbit determination scheme, and assuming that you have reasonable abilities to stabilize in direction of these things, you can get a polarization that is constant over the short period of observation, which are femtoseconds often, to 10 to the minus 40th radians. That is a very, very slight change in polarization. This doesn't mean you know what it is to 10 to the minus 40th radians. This simply means that it is constant over your observation period of time to 10 to the minus 40th radians. Okay, well the question is, all right, it's constant. maybe intervening material might somehow shift polarization to the point that this very precise constant polarization, you can sense some change. You don't have to sense its value, but some change. So let me look at that. Well, the systems that Fang-Yu Lee has been pioneering involve something called fractal membranes. This is one of the several references about that. They are very precise in polarization sensitivity, extremely so. They're probably good to maybe 10 to the minus 10 to 10 to the minus 15 radians. That is, they pass through polarization, sort of a polarization filter. These particular references are all given in the book. You can look at it. I just copied this one, this particular one now. Now, there's another, a little more recent work that's been done on supercooling mirrors. And some discussion here of how you might use it as a gravitational wave detection scheme. If you join this concept with the fractal membrane concept, in theory at least, you can see a differential, a change in polarization, not necessarily, again, measuring it, but simply saying something we know is quite constant, and now we see it changes a little bit. Okay, that changing a little bit is the kind of thing that you have when you go in and you get a full body scan. They're really not quite the X-ray. They're often looking for the polarization change, the spin changes in electrons and so forth. But the full body scan of these things does take into account a change rather than an actual snapshot or a picture of something. Now there's another approach to sensing very slight changes in polarization. And this is the basis of the Birmingham University high-frequency gravitational wave detector. This was developed by Michael Cruz, and Richard Ainley received his PhD a year ago, January 2006, there in building this. I have been not working with him, but observing what they were doing for the last several years, and I've seen this device. It's a little cleaner setup than when I was there a few years ago. It basically uses a concept of polarization, and if you put two of these, you can do a differential, difference in. And just like in interferometric work, you can find very high precision if you difference things. In that case, differencing paths of light. This is almost similar to this. It's a more complicated theory, and it'll take more time than we have here all week to explain exactly how he does this. But these are essentially waveguides. Gravitational waves come through the waveguides. They change the polarization of the microwaves in there very slightly. You essentially beat one of these against the other one and get a small difference. And so if polarization changes, then again, you can sense it. This, probably talking to Richard, maybe 10 to the minus 30th radian difference, this would sense. The problem with this detector, of course, is it does not, for the purpose of relic gravitational wave detection, which some of us will be, which I'll be discussing on Thursday, the sensitivity is not great enough. This is down to a gravitational wave amplitude of 10 to the minus 22. It's about as good as it can do, whereas you need somewhere between 10 to the minus 28 and 10 to the minus 32. Now, when I say that, that's a string. That's meters over meters. So if you had a yardstick that was, say, 10 to the 28 meters long, why, you get a meter change. If you have one that's a few meters long, the change might be in the order of a very small fraction of a proton. That, of course, is the problem with many of these gravitational wave detectors. But this one is based upon polarization and could sense a very small change. Now, obviously, it's a big step from a big piece of equipment like this, or from frozen fractal membranes, down to something where you're actually scanning and imaging and doing that kind of thing. Big step. But it's an engineering step, not a basic physics step. and engineering steps can, with the power of thousands of brilliant engineers working on it, they tend to be overcome much more rapidly than trying to redo Einstein's laws and things like that. The working hypothesis as an influence of mass on polarization. I just took this as, don't take any of this down, I did not put this in the paper because, but this, just to kind of give you an idea of numbers. This is what Misner, Thorne, and Wheeler in 1973 said: in the real universe, the space-time curvatures due not only to the energy of gravitational waves, but also more importantly to the material content of the universe, so on and so forth. It's difficult to establish theoretically exactly what that influence is, but let's just to see order of magnitude things that it might be. The solar mass is about 2 times 10 to the 30th kilograms. Suppose you had a cluster of 10 to the 7th stars, each having the mass of the sun, and suppose, this has not been tested because we haven't really been able to detect these things, suppose it causes a shift in gravitational wave polarization of a milliradian. Well, that's a suppose, but at least it doesn't light up any alarms saying, oh, well, maybe out there you can do this. Under that case, the change of polarization would be, for a 2 kilogram mass, would be 10 to the minus 40th radians. This is in the area that we're talking about. So it's not, of course it has to be proven. Of course there has to be laboratory experiments and so forth, but it's not a wild surmise that you might be able to sense a change in polarization, especially if the polarization that you're looking at is absolutely fixed, or at least fixed to 10 to the minus 40th radians. It's really a solid thing. So all you're trying to do is find a differential. So that's really the basic idea of this. So the conclusions are that a satellite-based surveillance system to image subterranean weapons of mass destruction or personnel of interest inside and behind buildings, deeply submerged submarines, oil and mineral deposits on the other side of the Earth, might even provide for acoustical surveillance or eavesdropping. It might defeat the recently proposed EM cloaking or stealth techniques. Maybe some of you have read these. If you think some of the ideas some of us have are wild, this reminds me of the Philadelphia experiment. They've actually gone through and proved that you can pass electromagnetic waves around objects and bring them back together the other side, somewhat like a slipstring around a ball, and never sense electromagnetically the device. And they built some of these, and there's quite a bit of literature on this, and I have some of it referenced in our book. You can look for hidden missiles and rockets. You can do a whole number of things. Let your imagination be your guide. It's important to recognize that LIGO and the other interferometric detectors, such as advanced LIGO, GEO 600, LISA, they can't detect high-frequency gravitational waves. Their technology is not even close to it. It's as far as the difference between the technology for a DC motor and a microwave oven. They are totally different. And that there is potentially a sensitivity to less than 10 to the minus 40th radians. And if this turns out, after experiment, to be true, then it opens up the whole idea of imaging, body imaging, the whole idea of a new surveillance system. Thank you.
Okay, we actually have 9 minutes for questions. Paul.
Bob, have you seen a situation required where you need imagery and stuff like that, people arguing over the priority? I can imagine all the arguments you have about having one radiation spot on the world. You probably have to get approved from the President of the United States and Congress to say, hey, I can use that spot. Is there, when you have an FBAR resonate, does that do just one frequency, or how would you generate more than one radiation pattern and have these patterns move around at will based upon?
Okay, and that's a good question I forgot to touch on. What you need is to change the timing between the two radiators. This is like going from a circular to an elliptical orbit, and you can do that in microseconds. So you can produce 1 million of these little things at a whole slew of locations all over over, under, and in planet Earth. So these, just by changing the timing, and the phase of them, you can change the focus point of them so they can be anywhere. And of course, it doesn't preclude having a couple of clusters or a couple of lasers at these points. But that only gives you like a factor of 2. But if you change their phase and timing a million times a second, you can produce their locales, a million different locales. If you have, say, 10 clusters and 10 lasers, then you'd have 10 million locales that you could do every second.
That's assuming that we have detectors that look.
Exactly, yeah.
Really taking into account those.
Yeah, and you have to, the objective detectors that Fang Yu Lee and the others in our little group here is looking at, we're aiming for 10 to the minus 32. That would allow us to, all theories of relic gravitational waves of the Big Bang, that is the smallest amplitude that is ever predicted. Gets up to 10 to the minus 28. So that's where we're all aiming, as I'll be talking about on Thursday. The first thing you do is you get a detector, and hopefully it detects relic. That then proves the detector. Okay. And then the question is, you can set up a generator and using the proved detector, see if you're sensing.
Okay, Vince.
Bob, that Birmingham student's experiment, you said he received his PhD?
At Birmingham. He's now in London. I think the University of London.
Presumably, if he received his PhD, his experiment was successful. The question is...
Well, okay, I see where you're getting. No, he did not sense. When I was there about 3 years ago, looking at his work, he felt there might be a way, those loops, anyway, you can remember what they look like. I don't know if I can find one right here. Those loops, if you made them superconductors, you could increase the cube somehow. Well, there were a lot of other factors, and they found out that 10 to the minus 22 is about the rest. But he had all his equipment working from the point of view of pseudo-gravitational waves going through it. Okay, and he worked and worked and worked, and now you're his, let's say, his PhD advisor. You find that there's absolutely no way he can get down to 10 to the minus 22, but he has a system that there exists high-frequency gravitational waves, which, by the way, we might be able to generate down to 10 to the minus 2. Through all the work he had done, it proved it out for that particular thing. Are you going to deny him his PhD? I don't think. As a member of the committee, I probably wouldn't. I'd say you've gotten something that ultimately might be of use. But no, if he had been able to detect relic gravitational waves, I'll tell you, he would have gotten a Nobel Prize almost instantaneously.
Well, yeah, that's why I'm curious. Usually, I mean, I know I had to change topics.
Well, he was way down the line. He had all this, and I must tell you another thing. His professor, Michael Cruz, he was the one that sort of had the idea. So now think about this a little bit. You've got a graduate student, and you have this idea of how to sense gravitational waves, and the graduate student goes away and develops something. Well, okay, Michael Cruz probably took a little bit of liberty, but it would have been a great embarrassment to him if this student who was carrying out his theory was denied the PhD. In fact, I don't think it ever came up. I had dinner with Michael.
More on the basis of the theoretical work.
Yeah, and I had dinner with Michael, and he would never. He's not that kind of a guy.
Any other questions? Yes.
Is there any possibility of combining this with your application you presented yesterday to provide real-time feedback and detection of the material you're actually affecting when nearby,
Exactly. Yeah. If you have non-invasive imaging techniques and also to be at the same time affect that site in the human body, quite true. You could do that. I mean, I think in the end, all surgery is going to be done by mechanically, robotically, with sensors and so forth.
So the power levels aren't too low?
It all depends upon the detector, but I don't think so.
Do you use superconductors to deflect any gravitational waves that are being used against you?
Well, yeah, but the kinds of things that Clyde Woods is doing, with a superconductor and deflecting them away, I would imagine. Now, by the way, the things that he's done are very important. When I talk about 10 to the minus 32 and 10 to the minus 28, this teeny-weeny stuff, potentially, Clyde could get an amplification of 10 to the 6th, or maybe even more. I mean, it's only limited by refraction of what he can do. And you could, with some of these superconducting materials, you could make astronomical, like telescope, maybe 100 meters across, maybe 1,000 meters across. You just pile up a lot of these little individual mosaics of superconductors. I guess the MGO something or other is fairly cheap, and do it. So there's lots of possibilities.
Yeah, I had a little bit of concern of the noise you pointed out on a previous slide, pointed out the sun could potentially provide some polarization noise. And so this reminded me of the solar eclipse anomaly that the Chinese had measured, where there's a little dip before the eclipse and there's a little dip after the eclipse. And it amounts to an annulus of gravitational dip around the sun that's picked up during the solar eclipse. So I'm wondering if that might be pointing towards, in their instrumentation, actually picking up on a polarization angle change versus an actual gravitational dip. I'm wondering if you had any comments about the solar
Okay,
eclipse.
the first thing is that, yes, I'm familiar with that, and that's the thing that leads you to the conclusion that maybe mass does change polarization in a significant fashion. That's very significant if that holds up. I was looking at something less. But this frequency is so different. We're here, we're talking about a hundredth or a thousandth of a hertz. Our things is megahertz, terahertz.
So at a high frequency, you know.
Okay?
Okay, we're out of time for questions. Thank you very much.